Good morning, sir. This is S. Jahnavi from CSC second year. And for CA assignment 2, my topic is B+trees and its operation. Brief introduction about what I'm going to cover in my presentation. First, I'm going to start with the introduction and then we'll look at what is structure of B+trees and then we'll see properties. And there are different operations in B+trees and we're going to look each one, that is search, insertion and deletion operations. And then we'll see the advantages and use cases like where these B+trees are used, and then we'll perform some considerations performance, and then we'll finally see the conclusion. So for introduction of B+trees. So basically B+trees are self-balancing tree data structure. This maintains sorted data, whereas in B trees there was like not in sorted order, but in B+trees the data is in sorted order. And here we can see that there are an extension of B-trees and are optimized for systems that read and write large blocks of data. So B+trees are widely used in databases and file systems due to their efficient data retrieval capabilities. So B-trees were only used in some fields, but B+trees are mainly used in database and file systems. Next, we have the structure of B+trees. So here I have represented a diagram which basically represents the structure. So every node consists of a data node and a pointer to its leaf node. So basically the point is that in B+trees the data is always stored in the leaf nodes, and the indexing or the pointers that has data in leaf node or in the internal nodes or parent nodes. So here it says the same thing, that a B+tree consists of internal nodes and leaf nodes. Only leaf nodes store actual data records. Internal nodes act as guides to help navigate the tree, containing keys and child pointers. So here the leaf nodes are linked together. So when we consider to B trees, the nodes are not at all linked, but in B+trees the leaf nodes are linked together. Actually this provides a efficient way to travel in the data in sorted order. Next, we have properties of B+trees. So mainly there are two main properties of B+trees. One is that all leaf nodes are at same level, ensuring that a tree is always balanced and the search times are predictable. And the second property is that the order of B+tree determines the maximum number of children each node can have, impacting its height and efficiency. So here there is another diagram that shows the structure of B+trees. So as I mentioned earlier, there will be a data node. Actually the upper layer is the internal node and the lower second layer is the leaf node. You can see here that the leaf nodes are linked together. The search operation. So in searching in B+tree starts at root and moves down to the leaf level by following child pointers. So basically search operation in B+trees, like for example I have given in the diagram. So let us consider that we are searching for a node with value 1, that is key value 1. So it basically starts at the internal node and compares the key value with the internal node value. So since 1 is less than 5, it will move to the left side of the node, and it again compares with the 3. So 1 is less than 3, so it again moves to the left side of the node. So at the last leaf node we will see that the 1 is present, so it represents that 1 is found in the B+trees. Likewise search operation is performed in B+trees. And next, insertion operation. So basically insertion operation means inserting elements or key values into the B+tree node, and this involves finding appropriate leaf node for the new key. It is similar to the search operation. So basically suppose here we must remember one point, that all the data must be represented in the leaf node itself, and those leaf nodes are connected through link. So suppose here we have 3 5 1 3 5 7 8. Suppose I want to insert 4, a value node with element 4. So it will check if 4 is greater than 3 or less than 3. Since 4 is greater than 3, it will move towards the, it will come under 5. So 4 will be inserted first and then 5. Likewise, insertion operation in B plus trees is performed. And there are some points like if the node is full, it splits into two nodes, promoting the smallest key to the parent node, which may also require further splitting. So basically, this splitting is based on the order that we have given. Suppose we have the order only 2, then if the third element is gonna insert in the same level, then the node will split. Likewise, insertion will be performed in B plus trees. And next, we have some basic formulas that we need to remember when we trying to solve or do a B plus tree problem. So first we have maximum children will be m and minimum children will be m by 2. Then maximum keys or m minus 1 and minimum keys or m by 2 minus 1. So these are the basic formulas, or you can say that statements that we need to remember to do any problem in B plus trees. Next we have deletion operation. So deletion in B plus trees begins by locating the key to be removed in the appropriate leaf node. So as I mentioned, it is very important point that all the data must be stored in the leaf node itself. So the deletion will be also performed in leaf node only. And so let us look what is the deletion operation. So if the deletion causes the leaf node to fall below the minimum accompany, it may merge with a sibling node. So merging can propagate up the tree, potentially requiring the deletion keys from internal nodes as well. So basically deletion is performed in three ways. So the first one is if the element that you want to delete in the node is less than minimum keys, then it would borrow the elements from its neighboring siblings. And if the element that you want to delete is in the node is greater than minimum number of keys, then it will simply delete it. So likewise, deletion operation is also performed in B plus. And next we have advantages of B plus trees. So we have wide range of advantages. First one is that it provides efficient search, insert, and delete operation, typically in a logarithmic time. So they are particularly suited for disk-based storage systems due to their reduced height and bulk loading capability. Next, the main advantage is that the linked leaf nodes allow for efficient range queries, making B plus trees ideal for database indexing. So this main advantage of B plus trees in database is due to their indexing, which makes it very easy and efficient for accessing the data, and it keeps the data in sorted order. We have the use cases. That is, these B plus trees are commonly used in database management system to index records for fast retrieval, and file system often use B plus trees to manage files and directories, ensuring efficient access to data. As I mentioned, B plus trees are widely and mainly used in database management and in file system also. And many search engines utilize B plus trees to handle large volumes of data and support search operations. And next, conclusion. So let us once recall the points that we have discussed in our presentation. Is that first of all, a B plus tree is a efficient data structure which consists nodes, and these nodes are connected or linked through links. That is, linked list is used to connect these leaf nodes, and the internal nodes are used for indexing, and the leaf nodes are the actual nodes that store the data. So here also the same points are mentioned, that B plus tree are powerful data structures that balances efficiency and performance in data management. And understanding B plus trees is essential for optimizing data retrieval and storage in computer science. So this is my conclusion. Finally, thank you very much for listening.